Global industries are accelerating their transition away from fossil fuels, and the pressure of that shift is falling squarely on hydrogen. By 2060, global demand is projected to reach 40 million metric tons annually. Meeting that demand relies almost entirely on one incumbent technology, steam-methane reforming, producing what the industry refers to as gray hydrogen. The reliance on this method comes down to sheer economics. Reforming natural gas drives the cost of hydrogen production down to a highly efficient 90 cents to $1.78 per kilogram. But that low cost masks a severe thermodynamic penalty. Breaking apart natural gas requires massive amounts of thermal energy. Exposing methane to steam at extreme temperatures oxidizes the carbon, releasing vast quantities of CO2 as a direct byproduct. The current alternative is green hydrogen, produced by splitting water molecules using electrolysis. It emits zero carbon, but it relies heavily on continuous, massive inputs of renewable electricity. That massive electrical requirement pushes the cost of green hydrogen up to $3 to $8 per kilogram, crippling any chance of widespread industrial adoption at scale. The energy sector is caught in a trap. Scaling hydrogen production currently forces a choice between cheap, heavily polluting thermal cracking or clean, economically restrictive electrical splitting. The problem is rooted in the physical chemistry of natural gas itself. The carbon-hydrogen bonds in methane are exceptionally stable, meaning shattering them historically requires extreme thermal energy. Bluerats Energy Formulations has proposed an alternative process to isolate hydrogen, one that circumvents the need for extreme heat entirely. Their approach relies on photochemical activation. Instead of applying raw thermal energy to a system, specific wavelengths of light are introduced to force chemical reactions at near room temperatures. Specifically, they use the photosensitized dissociation of hydrogen. This mechanism extracts hydrogen directly from methane gas without ever raising the temperature. By bypassing the intense thermal oxidative environment of steam reforming, oxygen is kept completely out of the reaction, which means no carbon dioxide is generated as a byproduct. Replacing industrial fire with targeted ultraviolet light changes the basic architecture of hydrogen production. This method captures the carbon atom in a stable, physical form instead of venting it into the atmosphere as a pollutant. To execute this low-temperature process, the system requires a specific catalyst to interact with the incoming light, mercury, Hg. In its standard ground state, vaporized mercury is chemically inert and will not interact with the surrounding methane gas. The activation sequence begins when the system is struck by specific wavelengths of ultraviolet light, designed to photosensitize the mercury. The mercury atom absorbs the photon's energy directly. It loses an electron to the excitation process and enters a highly energetic excited quantum state, denoted as Hg star. This immense absorption of energy happens strictly at the atomic level. The kinetic energy is contained entirely within the individual mercury atoms, keeping the overall ambient temperature of the reactor incredibly low. The UV-activated mercury functions as a microscopic energy transfer agent. It carries exactly enough localized force to break a molecular bond, eliminating the need to heat the entire industrial facility. Once activated, the highly charged mercury atom physically collides with a stable methane molecule, transferring its stored energy directly into the structure of the gas. This sudden transfer of energy causes homolytic cleavage. The impact cleanly snaps a single carbon-hydrogen bond, splitting the molecule into a volatile methyl radical and a lone hydrogen radical. Having transferred its payload, the mercury atom is completely drained of its absorbed UV energy. It returns to its baseline ground state, ready to absorb another photon and repeat the loop. What follows is immediate radical recombination, a secondary reaction phase that resolves these unstable fragments in fractions of a second within the low-pressure environment of the reactor. In the vacuum, two wandering hydrogen radicals find each other and merge to form stable hydrogen gas. Simultaneously, the orphaned methyl radicals merge with one another to form a larger, stable molecule, ethane. This highly specific two-step sequence, cleavage followed instantly by recombination, achieves the primary objective. It strips out pure hydrogen gas while safely locking the leftover carbon into a higher hydrocarbon chain. Moving from theoretical chemistry to applied engineering requires a specialized physical reactor to house the process. This diagram details the conceptual reaction chamber design. Component number 7 on the left is the critical external light source. Its sole function is to continuously fire through the window and bombard the gaseous mixture inside with UV photons. For the radical recombination to occur efficiently, the chamber must maintain extremely specific environmental parameters, operating at a very low pressure of approximately 10 millimeters. Engineering the system requires overcoming the historical bottleneck that previously halted this specific technology in laboratory settings: exceptionally low quantum yield. Early 20th century studies recorded a dismal quantum yield of just 0.004 at 98 degrees Celsius. Thousands of photons were expended and wasted for every single hydrogen atom successfully produced. The secondary failure of these early attempts was physical containment. Free hydrogen atoms were frequently lost to chaotic side reactions, bonding with olefins before they could successfully form stable hydrogen gas. Recent proof-of-concept testing by Bluerats has optimized the primary quenching process. Their modern reactor iteration has demonstrated a confirmed measured hydrogen yield of 2.6%. While a 2.6% yield proves the chemical pathway functions in reality, thermodynamic simulations indicate that further hardware optimization could push yields toward 10%, the specific threshold needed to make the system industrially viable. The true economic viability of this reactor hinges directly on the secondary reaction, the higher hydrocarbons produced alongside the hydrogen gas. As methyl radicals recombine, the reactor generates complex byproducts, including ethane, propane, and hexane. These compounds are highly valuable, readily converting into sustainable biofuels like ethanol. The most lucrative offshoot is ethylene, a raw material directly utilized in manufacturing environmentally friendly bioplastics. Compare this output to the traditional steam reforming process, where industrial plants incur massive financial penalties and logistical costs just to manage, capture, or vent their waste carbon dioxide. By monetizing the captured carbon fraction as feedstocks for green plastics and biofuels, the production facility generates its own secondary revenue stream. The byproducts effectively subsidize the per kilogram cost of the primary hydrogen yield. Operating entirely at low temperatures gives the photochemical reactor a massive logistical advantage. It functions completely without the towering thermal columns, heavy furnaces, or high-pressure steam lines required by traditional plants. This minimal physical footprint allows for decentralized modular deployment. Complete reactors can be installed directly at active natural gas exploration sites to process the fuel at the source. Because the reaction relies on low-pressure operational requirements, the hardware is perfectly suited to plug directly into existing bio-CNG generation facilities. The immediate infrastructural benefit is integration. Operators can install these units at existing pipeline blending points, using already installed compressors to mix the newly generated green hydrogen directly into regional natural gas streams. Blending this specific output of hydrogen actively increases the overall calorific value of the natural gas supply before it ever reaches the end consumer. Photosensitized methane dissociation represents an elusive middle path for energy transition. It leverages our ubiquitous, pre-existing hydrocarbon infrastructure to produce clean, high-yield hydrogen without ever having to light a fire.